Hi class, we're on to week 6, lab 6 of Chem 111. This week's lab is to determine the water of crystallization of copper 2 sulfate. Please note you have a pre-lab assignment due at the start of lab. You can find this on the previous page of your lab manual. It's on page 32. You have to have this completed before coming to lab, as well as your pre-lab lecture worksheet and setting up your lab notebook. So let's get started to go over the topics necessary for this experiment. As always, please make sure you've read through the entire procedure and introduction carefully before listening to this video so that it actually makes some sense. So we have a few overall goals for this week's lab. The first goal is to find the formula of the hydrate, and we'll define what a hydrate means momentarily. The hydrate you'll be working with in this lab is copper 2 sulfate. We don't know what X is, and the goal of this lab is to determine the moles of water, X, in this formula of the unknown hydrate. Another goal is to calculate the actual percentage of the water in the hydrate, calculate the theoretical percentage of water in hydrate, and calculate the percent error of water in your hydrate. It's a lot of calculations. Please make sure that you review chapter 9 in addition with this pre-lab lecture video to help you prepare a little bit better for this experiment. So let's go through the general topics necessary for this lab. A hydrate is known as an ionic compound that contains water molecules in its structure. Now, these water molecules are not necessarily bound to the structure, but they're actually absorbed onto the surface of the structure. If we have a hydrate, we then also have an anhydrate, which is the substance that remains after the water is removed from the hydrate. So as you'll see in lab, you're going to be heating the hydrate. So when we heat the hydrate, the water molecules are driven off as steam, leaving behind the anhydrate. So here's a great cartoon showing this illustration. We have, for example, here we'll pretend that this is the copper sulfate molecule compound, and it's a hydrate, which means it's surrounded by water absorbed onto its surface. So this is our hydrate. We then apply heat, which you'll be doing in lab this week using a crucible and a Bunsen burner flame. So here we have a great setup for you of what you'll do. Please make sure, and your lab manual goes over this, to crack open your crucible, otherwise it may actually explode because of the amount of energy being released. So when we heat our hydrate, we release the water molecules, so then we have our anhydrate and water vapor, which you may actually see come off as steam in lab. So chemically, what's going on here? So here we have our hydrate, which is copper sulfate H2O, and this is a solid. You're going to see that it's a solid in lab. We supply heat, and sometimes we show that by writing heat over our reaction arrow. That will yield us copper sulfate, and now this is copper sulfate free of water molecules, so this is our anhydrate plus H2O, and water vapor is gaseous water. So the experimental portion of this lab is relatively straightforward. It's actually quite quick. The biggest thing about this experiment is really all the calculations that you have to do, and really taking proper care in how you record your observations. We're going to have lab rubrics, grading rubrics, as always, as we do with every experiment, so it might be a good idea to actually look at what's expected of you for this lab. So I'm going to go over an example of how to find the formula of the hydrate, and this will resemble very closely what you'll actually do in lab. So first, let's go over step-by-step instructions on how to actually find the formula of your hydrate. So first, you want to record the mass of your hydrate. Next, after heating, and I'm going to write this out, and I hope you're careful, follow the procedure in detail. As with every experiment, if you don't follow the procedure in detail, you're most likely going to get something incorrect. So after heating, and of course follow the procedure in detail, determine the mass of the anhydrate that remains. Meaning, just measure your anhydrate after your crucible has actually cooled down to room temperature. The third step, the mass of the water is calculated, the mass of the water that's actually present or was present is calculated by finding the difference between the mass of your hydrate and mass of anhydrate. And that makes a lot of sense. Basically, if we look at this cartoon, we're taking the mass of the hydrate, we're subtracting the mass of the anhydrate, and that will give us the mass of the water. So formula-wise, this is what we have. So mass of H2O present is equal to your mass of hydrate minus mass of anhydrate. All right, fourth and the last step, the mass of the water and the mass of the anhydrate are each converted to this unit called moles. And we will go over this in chapter 9. I will also go over this in this lab lecture video so that you are fully prepared for lab. The mass of the water and the mass of the anhydrate are converted to moles, and we do this conversion using their respective molar masses. Again, molar masses is covered in chapter 9, so again, it's really crucial that you actually read chapter 9 for this experiment. It's important that you get a whole number ratio. So if you get a fraction of a number, resolve that by either rounding up or rounding down. We're going to be doing an example with this momentarily. I just want to go over moles and molar masses, etc., before we actually do a physical example with you guys, an actual calculated example. So as we'll go over in lecture, or if you've already gone over in lecture, the mole is a unit for counting particles such as atoms, molecules, or ions. It's also used to relate the mass of an element in grams to the number of atoms it contains. So it's basically a counting unit. Just like we have a dozen as a counting unit, moles are a counting unit. If you recall, we learned last week about balancing chemical equations. So let's actually interpret what this chemical equation says. This equation can say the following: one hydrogen molecule and one iodide molecule react to give 2 molecules of hydrogen iodide. This same reaction also says 1 mole of hydrogen molecules react and 1 mole of iodide molecules react to give 2 moles of HI, hydrogen iodide molecules. One thing that's important to note is that we can't actually measure moles or molecules in lab. We can't actually do that. So what we do in lab instead, so these coefficients, it's basically saying 2 moles. When we don't have coefficients, it means our coefficient is 1. So 1 mole of X molecule. Since we can't actually measure moles or molecules in labs, we use this concept of molar mass, which allows us to convert from moles to grams. Molar mass, if you recall, we briefly introduced this in chapter 2 and chapter 3, is the mass in grams of a substance that is numerically equivalent to the substance atomic mass. And we talked about atomic mass in chapter 3. So what does that actually mean? Basically, we know under our periodic table, we have our atomic mass. The atomic mass, if we were to read this, is basically saying you have 1 mole of hydrogen atoms has a mass of 1.0079 grams. So our molar mass, let's write this out in an actual useful manner, is 1.0079 grams per mole. Similarly with carbon, we know that this is our atomic mass. So our molar mass for carbon is 12.011 grams per mole, and for uranium is 238.029 grams per mole. So as I said, you can't actually measure moles or molecules in lab. So what this basically means is that you're going to need to use unit analysis, which we covered extensively in chapter 2, to be able to convert from grams to moles and moles to grams. And how do we do that? Remember our handy equation of your given times your desired over your given gives you the thing that you're desiring. Again, we'll do examples of that at the end of this lecture video. So unit analysis comes back heavily in this chapter. Let's also review what subscripts say, because a lot of you are still quite confused about that. So we have a CO2 molecule. The molecule message says you have, in one CO2 molecule, you have 1 carbon atom per 1 CO2 molecule. You also have 2 oxygen atoms, because our subscript here is 2, per CO2 molecule. Now the mole message says you have, in a CO2 molecule, you have 1 mole of carbon atoms per 1 mole of CO2 molecules. How do I know it's 1? Because there's no subscript, right? And for oxygen, our message is 2 moles of oxygen per 1 mole of CO2 molecule. How do I know it's 1 mole of CO2 molecule? Again, because there's no number in front of it. So how do you calculate molar mass when you have more than 1 element? So our periodic table gives us our molar masses right under the elements. If you have a compound, to calculate the molar mass of a compound, in this case, let's do molar mass of CO2, you basically take the molar mass for each of the atoms, multiply it by the subscript, add it to the molar mass of the other atom, multiplied by the subscript. So our molar mass for carbon is 12.011 grams per mole. I'm not going to multiply it by 1 because we know something multiplied by 1 is the same thing. Plus, now we have 2, because our subscript for oxygen is 2, times 16.00 grams per mole, which is the molar mass for oxygen. This is directly on the periodic table, so this is for carbon, this is for oxygen, and you should get a calculated molar mass of 44.011 grams per mole. That's your molar mass for CO2. So this comes very handy when we need to convert between grams to moles or moles to grams. So if I give you moles of something, of a substance, in a chemistry lab, you can actually measure it out only if you do this conversion to figure out how many grams do I actually have. All right, let's go over an actual example that's very similar to what you're going to have in lab, but of course using different substances and of course using different numbers. So we have a calcium chloride hydrate. So similar, you have a substance and it's surrounded by water molecules. That's what a hydrate is. It has a mass of 4.72 grams. After heating for several minutes, the mass of the anhydrate is found to be 3.56 grams. Find the formula of the hydrate. This is one of the goals of this week's lab. Let's go over the using the step-by-step instructions that I gave you in the beginning of this lab lecture. Okay, so our first step was find the mass of the water driven off. So find the mass of the water driven off. Okay, so we know that the mass of the water driven off is my mass of hydrate minus mass of anhydrate. Okay, so in this problem, they told us our mass of hydrate is 4.72 grams. Also remember, watch out for, can anyone guess? Sig figs. You can't forget about them. So here we have 3 sig figs, here we have 3 sig figs, which means our final answer is in 3 significant figures. Remember, don't round up early, keep them all until the very end. So here we have to find our mass of water driven off, so our mass of hydrate minus our mass of anhydrate, which our problem tells us it's 3.56. You're going to actually be measuring these components in lab. So your mass of water driven off is 1.16 grams of water lost. Let me just confirm this calculation real quick. 4.72 minus 3.56, 1.16. All right, our second step is convert mass of anhydrate to moles. And remember, based on the concepts that we just covered, we do this using molar mass, and I'm going to abbreviate molar mass as MM. So our molar mass for calcium chloride, we have to look up the individual molar masses for each of these components. For calcium, it's 40.08 grams per mole, plus 2 times, because chlorine atoms are 2 times 35.45 grams per mole. So our molar mass of calcium chloride is 110.98 grams per mole. So to convert our mass of anhydrate to moles of anhydrate, our mass of anhydrate is 3.56 grams times its molar mass, but I want my desired unit is moles, so it's actually 1 mole over 110.98 grams. So it's actually 1 over the molar mass. Your grams cancel out, so this is my given over desired, given times desired over given. And if you do this calculation out, it's 0.0321 moles. Why am I interested in finding this? Because if you remember from our instructions here, the last step is to find the ratio of moles of water to the moles of anhydrate, and that actually gives you the X, this X in the formula of the hydrate. Okay, so that is my moles of CaCl2 anhydrate. Okay, the next step is convert the mass of water lost, H2O lost, to moles. So similarly, we're going to do this using molar mass. So our molar mass of water is equal to 2 times 1.01 grams per mole. So that's 2 times the molar mass of hydrogen, which is 1.01 grams per mole, plus the molar mass of oxygen. And this will come out to 18.02 grams per mole. So let's do this out. We found out here that our mass of water lost is 1.16 grams, are given, times desired over given. We're desiring moles, so therefore 1 over the molar mass, or otherwise 1 mole over 18.02 grams. These cancel out, and you should get 0.0644 moles of H2O lost. Our final step is to find the moles of H2O to moles of calcium chloride ratio. So what does that actually mean? It's literally moles of H2O divided by moles of anhydrate calcium chloride. This, let me put an insert here. This is your anhydrate, not your hydrate. Okay, so let's just plug in our numbers. So it's 0.0644 moles of H2O divided by our moles of calcium chloride anhydrate, 0.0321 moles CaCl2, 0.0644 divided by 0.0321, and you should get 2.006 moles of H2O over 1 mole calcium chloride. Now remember, this has to be a whole number ratio, so that means this we round to just simply 2, so therefore it's 2 moles of H2O per 1 mole of calcium chloride hydrate. So therefore the formula of calcium chloride times X water, we just found out what X is. Your formula, now we know there's 2 moles of water per 1 mole of calcium chloride. So it's calcium chloride times 2 moles of water. 2 moles of water, remember this is, the unit is moles, 2 moles of water per 1 mole of calcium chloride. Let's write this out so that you guys understand what we're actually looking at. 2 moles of H2O are combined or absorbed with every 1 mole of calcium chloride. Let's write out our chemical reaction. So here we have calcium chloride times calcium chloride, really the way we write this, say this is calcium chloride dihydrate. Di because of the 2. It's a solid. This is our hydrate. We supply heat to it. It dries off the water and it leaves behind our anhydrate, calcium chloride, and 2 moles of water, and it gives off as steam, water vapor. Okay, so that is one set of the calculations that you're going to have to do for this experiment by, first of all, conducting the experiment, collecting all the data necessary, and then going through something very similar to this. So if you don't already, you have to make sure you actually bring your lecture worksheet with you, pre-lab lecture worksheet with you, so that you can successfully take care of this. So the other calculations that are necessary, so if you actually go into your lab manual on page 35, these are all the calculations. You'll actually be graded on these calculations. Basically what I've just gone through is the first, let's see, it's the first 6 steps of the calculations. Now let's go through steps 7 through 9 using the same example that we just had in our pre-lab lecture. So calculation number 7 is asking us to figure out the theoretical percentage, otherwise known as theoretical yield. The theoretical yield is defined as the maximum amount of product you can make from a given amount of reactions. So here, the theoretical percent of water is defined as, in this case, the molar mass of H2Os in, for our example, calcium chloride dihydrate over, oops, this is 2, over the molar mass of your hydrate, which is molar mass of calcium chloride dihydrate times 100. This gives you the theoretical yield of water, or the theoretical percent of water in your compound. So here we have to actually calculate the molar mass of our hydrate. So let's actually take this up here. Molar mass of calcium chloride dihydrate is equal to the molar mass of calcium, and I'm going to leave out units just for the sake of space here, plus the molar mass, 2 times the molar mass of chlorine, and again I'm getting all of these from the periodic table, plus now here I have 2 moles of this molecule. So let's open brackets, Actually, let's do it a simple way. Let's first find the molar mass of water, which we already did on the previous page, which is 18.02 grams per mole. So it's 2 times the molar mass of water. So 2 times 18.02 grams per mole. If you did all this math out, you should get 147.02 grams per mole, which is the molar mass of calcium chloride dihydrate. Please feel free to pause this video at any one point to catch up and to really understand what the calculations that we're doing. So let's fill in what we have here. The molar mass of waters in calcium chloride dihydrate, we have 2 moles of water here, so it's actually 2 times 18.02 grams per mole over the molar mass of your hydrate, which we just calculated it to be 147.02 grams per mole. And whenever you want to find a percent of something, you multiply that by 100. So you should get 24.5%. That's the theoretical yield of water produced, or that theoretically can be produced from this hydrate. Let's do our actual yield, in other words, measured percentage, what you actually produced. So the actual yield is the amount of product actually obtained. Theoretical yield is, in a perfect world, if our experiment went perfectly, this is the maximum amount of water obtained. So let's go ahead and calculate our measured percent of water. That is our grams of H2O lost over the grams of hydrate times 100. So in our previous page, we calculated our grams, this is 1/6 of H2O lost over 4.72 grams of my hydrate times 100. So you should get 25.0% of water actually obtained. This calculation is similar to what is being asked of you for calculation number 8 in your lab manual. Calculation number 9 wants us to calculate our percent error. So our percent error is defined as our measured value minus our theoretical value over theoretical value. And since we're trying to get a percent, it's 100. Now I've skipped a couple steps here. You could first calculate this ratio, which is 0.245, then multiply by 100. Similarly, you can do that here, 0.25 times 100. So that's really pretty much it for this experiment. A few experimental logistics. Don't forget your pre-lab assignment is due at the beginning of your lab section. We will not accept any late assignments. This lab is done individually, so please follow instructions very carefully. Do not heat the closed crucible, that's very dangerous. Tilt your crucible cover, and we show you a schematic of what we mean here. Tilt it slightly. Make sure you record your actual masses. I can't emphasize this enough. Your data will be completely inaccurate if you don't. So recording actual masses, whatever shows up on your balance is what you have to write down. Always note your observations. Make sure you indicate color change pre and post heating, etc. Don't just write same. You have to describe what it actually looks like. You're going to be graded on your calculations for this lab as part of your lab notebooks. 9 out of the 25 points are calculations. You have to complete these before leaving lab. Please note we actually do not have a post-lab quiz this week. Instead, we have a post-lab assignment, and this will be due the following lab period. Again, we won't accept late assignments. Copies of your post-lab assignments will be placed in lab, so no need, save your copy money. There's no need to actually print it out yourself. One thing, please include your units in all your work and watch out for significant figures. Points will be taken off for significant figures and not including notes. As always, if you have questions, please reach out to me or to your lab instructors. Good luck.